Okay, so we're going to talk about boosting, and it's not too much different than random forest in concept. It's just in the details, it's significantly different, and in some sense, it's sort of a mirror image of the bagging procedure. So where bagging, the basic idea is that we randomly augmented our data, right? So we did this random data augmentation using the bootstrap. Now boosting, the basic idea is we're going to do adaptive data augmentation. So we're sort of pushing some of the learning responsibility to the data augmentation method. Right. So how can we think about this? Well, if we have a data set, let's draw pluses and minuses. Let's draw two. So I'm just going to have a little vignette of a data set here. So if we start with, for example, some data set, just throw some pluses and minuses here, and then we have a bunch of minuses. Maybe we have a lot more minuses over here, maybe many minuses over here, and a scattered group of minuses here, right? So suppose this is our data set, and then we were to train a very simple decision tree. So let's just say it's a single split. So perhaps the way we would split our data would be down along this line, and we would say that everything on the right-hand side is predicted minus, and everything on the left-hand side is predicted plus. Then what boosting, the way boosting works, is that it's going to now downweight those which were correctly classified and upweight those which were incorrectly classified. So at the next stage, we have all of the correct classified points are downweighted. Oops. One of those blue. Boop, 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 boop. And these are correctly classified as well. Here. Let's do, and then the incorrectly classified ones are going to be upweighted. Bep, bep. Bep, bep, bep. Boop, 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 boop. Right. So we have these misclassified points are now going to be upweighted, and then if we train a new classifier on this, we might, on this weighted data set, we might then in turn get a different classification algorithm. So for example, classifier. So for example, this split would then perhaps do a better job of separating out the blues from the reds after we do this data augmentation. Now, how do we aggregate in boosting? Well, it's going to be the same as how we aggregated in bagging. It's going to be a weighted average or a weighted sum of the different classifiers. But the idea behind AdaBoost is that this weighted sum is in fact going to be, the weights are not going to be the same. So for AdaBoost, the AdaBoost algorithm, it works like the following. So in this case, we're going to make yi be in -1 plus 1. So we're going to just be talking about binary classification for this setting. So let's just initialize some weights, wi being 1 over n. So these are the individual points weights, I going from 1 up to n. Right? And now for little b in 1 up to big B, we're going to do the following. we're going to fit. So this is for each different classifier. So in each step, we're going to fit classifier to the training data. So these are the yi's, xi's, with our weights, wi. And so if we have weights, we can just use those to weight our misclassification loss, our 0-1 loss, for our stumps. These simple decision trees with a single split are called stumps. So typically we choose something that is called a weak learner or a weak classifier, such as stumps, which is low depth decision trees. And this thing produces our f hat b, our predict method. And now, after we do this, we need to figure out how much we're going to weight f hat b. So let's compute our weighted misclassification error. Weighted misclassification error. And this will be epsilon b is equal to the sum over I of this weight for the given point, yi, which is not equal to y hat bi, if this is the prediction. And this is over the sum over I, wi. So this is just a weighted, this is just the misclassification error when a point is weighted by proportional to wi. Now we have to take this and we have to set our alpha I equal to, alpha sub b equal to log odds of misclassification, which is 1 minus, or of correct classification actually, but still log odds. So we set this alpha b to be this, and this is going to be our weight for that predictor, and then we have to update the weights for the individual points. So wi gets wi times the exponential of alpha sub b, indicator that yi is not equal to y hat bi. Okay, so far so good. Now, first of all, this y hat bi, I was a little bit cavalier about talking about this, but the y hat bi, because we're doing binary classification, this is just going to be defined to be the sign of this f hat b of xi. Right? So that's just a note. And that fully describes the algorithm thus far. Now at the end of the day, we are going to update our weights, retrain our classifier, compute these things, and then at the end of the day, we have a list of alpha b's and f hat b's, right? The classifiers and their weights, the trained classifiers and their weights. So now, finally, we can create an f hat of x, a predict method, which is just equal to the sum over b equaling 1 to capital B of alpha sub b times f sub b of x. And our final classifier is y hat of x is equal to the sign of this f hat of x. This is the final predict method. So, what do we do? What are the sort of characteristics of the base classifiers that we would like? So in bagging and in random forest, we wanted a classifier with low bias, but perhaps high variance. So we grew a very deep decision tree. Here, the opposite is going to be true. because we are doing this data augmentation, and that is what's going to reduce our bias, because we're going to start to highlight the misclassified points. That's going to reduce our bias. We want a base classifier that just does effectively some learning, but it might not be great at learning. It might not have an excellent, a very low bias, but it does have a low variance. So we want to actually offload the responsibility of having a low variance to the classifier itself, what we call this weak learner or the base classifier, this f hat b. And then we want the responsibility of having a low variance on the weak classifier, and the responsibility of having a low bias is offloaded to this adaptive data augmentation procedure. So I won't go too much into that, but I will mention a sort of miraculous thing that happens, which is a proposition that says that the training error of AdaBoost is bounded by the following, which is e to the -2 sum over the b's, going from 1 to capital B, of this gamma sub b squared minus epsilon b. So let's say that over again. This gamma b is equal to 1/2 minus epsilon b. If you look at epsilon b, this is the weighted misclassification error, and so this should be if 1/2 minus epsilon b is positive, that means your probability of correct classification, this weighted probability of correct classification, exceeds your weighted probability of misclassification. And so as long as your learner is doing better than random guessing on the augmented data every time, then your training error is going to continue to go down. So our goal is to have a classifier that can just give us something that gives us better than random guessing at every time. And so a stump, a very short decision tree, could actually achieve this. Now, one caveat with boosting is that there's actually some restrictions to what it could learn. So, for example, suppose that we had the XOR data set, which looked like 1, 0, 0, 1 here. And then suppose that for whatever reason, we chose our initial classifier to split down the middle here. And then we just predicted this to be 1 and this to be 0 here. Now, what happens in the data augmentation, right? Now with the data augmentation, we would have a, this is a misclassification, this is a correct classification, so it's downweighted, correct classification and misclassification. Oops, the other way around. Misclassification here and correct classification down here. Okay, so the next thing that we would probably do is split down the middle again and weight this to be 1 and this to be 0, right? Or predict this side to be 1 and this side to be 0. And then you're back to square 1. Right? You're back to square 1 where you have everything being equally weighted. Okay, so what happens is that when you do this averaging, you get something that is when you do this averaging, you get something that is effectively a net zero classifier. So it's just going to be random guessing if you applied this guessing. And if you think about all of the possible classifiers that can be achieved via via weighted average of stumps, well, you could make a split here. And for example, you could predict here 1 and here a 0. You could make a split here, right, and predict a 1 up here and a 0 up here. And you could also, for example, swap the roles of 1 and 0 for these classifiers. But there's actually a very limited number of possibilities here. you can have, for example, 2 up here, 0 down here, a 1 here, and a 1 here. That wouldn't learn XOR, right? You could try to say do a minus, subtract, like take this classifier, subtract this classifier from it. Then you would get, for example, 0 up here, right? Because 1 minus 1 is 0. But then you would get 0 minus 1 is minus 1 here. You would get a 1 here, and a 0 here, because 0 minus 0 is 0. And that also wouldn't learn XOR. And actually, you can just exhaust all possibilities, or you could prove it more rigorously, but XOR cannot be learned from boosted stumps. Now, of course, if you had a decision tree that could learn XOR, which would be a depth 2 decision tree instead of a depth 1 decision tree, then you could learn XOR from boosting, because one of your base learners can learn XOR. Boosted stumps with 1 split. Okay, so that's a caveat about boosting, is that it actually has there's some restrictions in what functions we could learn.